Alright, so I'm going to do some of the problems from the mixed calorimetry problems. I'm going to start off with number 4. Number 4 says calculate the amount of heat necessary to vaporize 1 gallon of gasoline. The density of gasoline is 0.730 grams per milliliter. And we have 1 gallon. Heat of vaporization of gasoline, so that's delta H of vaporization, is given as 349 joules per gram, and 1 gallon equals 3,785 milliliters. And it wants to know the amount of heat necessary. Alright, so first thing we need to do, since they gave us the heat of vaporization and there's no delta T, and it says it necessary to vaporize 1 gallon of gasoline. So we're going to be using Q equals, and since they gave our delta H in grams, we're going to use M delta H. So this is grams because this was given in joules per gram. So I don't have grams right now. I have density and I have volume. So my first thing I can do is solve a density equation for mass. So I take my 0.730 grams per milliliter equals M divided by 3,785 milliliters. So to solve for M, I'm going to multiply them together, and that is going to give me, let's see, 0.730 times 3,785. So I'm going to get 2,763 grams. So now I can plug it into my equation. So I have 2,763 grams times my delta H, which is 349 joules per gram. And now you see why it was okay for us to use grams here. It's because this is in grams, and now they cancel out. And I'm left with joules, which is what I'm looking for. So if I do the multiplication, it gives me Q equals 964,287 joules. And that is my energy needed. So let's take a look at another one. We'll take a look at number 11. Alright, so number 11 says determine the amount of energy absorbed by 2 liters of water as it's converted to steam at its boiling point. Alright, so once again, we have no delta T, and what we need to see here is that it's not saying that water is heated up to a temperature, it's just saying it's at the boiling point and it's going to steam. So if this is water, we have 100 degrees Celsius. So it's saying that water is at the boiling point and that we are going to convert it all to steam. So we're going to go through this whole section right here and end here. because it doesn't say that we heated the steam up, it just says we made it all into steam. So we have one section, and all of these plateaus are our Q equals N delta H, or depending on the delta H, it can also be mass times delta H. Now since it's water and they didn't give you any delta H, you're going to use the one on the sheet I gave you. So we're going to have to convert our 2 liters. So if you don't know that 2 liters of water equals 2 kilograms or such, we can convert it to milliliters. So we get 2,000 milliliters. Now the density of water is 1 gram per milliliter. So that's why we can say that 2,000 milliliters of water gives us 2,000 grams. So once I have my grams, I'm going to use my Q equals N delta H because I'm going to use my molar heat of vaporization off my chart. So I have grams, and to convert that to grams, I'm going to divide by the molar mass of water, and then I'm going to multiply all of this by 40.7 kilojoules per mole. So that's off my sheet. And when I do that, I get 4,522.2 kilojoules. And we can just leave in kilojoules since it didn't specify any different. Alright, let's go back and take a look at number 5. We'll do this one. Sorry, number 7. So number 7 says the heat of combustion of gasoline is -4, so that's delta H combustion, is -4.40 times 10 to the 4th joules per gram. Remember, I had you take off the degrees Celsius. How many grams of gasoline are burned in a calorimeter containing 3,000 milliliters of water? And the temperature went from 25.5 to 46.5 degrees Celsius. So this takes place in a calorimeter, so that means that one thing is going to be giving off heat, and then something else is going to be gaining that heat. So when we have that situation, we're going to have our negative Q equals Q equation. And for this, you can have MC delta T of the one that's losing it equaling MC delta T of the one that's gaining it. You can have N delta H of this one equaling N delta H of this one. You could have N delta H of this one also equaling MC delta T of this one. And just because these are different, they're both equal to Q, right? So Q equals MC delta T, but Q also equals N delta H. They're different ways based on the situation to get Q. So that's why we can still set the two different ones equal to each other. So first we need to determine what information we have and what we can do with it. So we're going to take a look at this. We have delta H of our gas, and we're looking for grams. And since our delta H was given in grams, we know one side is going to be Q equals M delta H. And then over here, we're given volume of water, which we can convert into 3,000 grams. And then we have a temperature change, and we know the specific heat of water is a liquid. So over here, we're going to use MC delta T. So our final setup's going to look like this. Oops. So the one that's going to be losing the heat, and in a combustion reaction, that's going to be the one that's burning. So we're going to have our grams of the gas times negative 4.40 times 10 to the fourth joules per gram equal to my mass of the water, the specific heat of water, which I'm going to use my 4.184 joules per gram degrees Celsius, and our temperature, our final minus initial. So here's how we're going to set it up. Now this one's pretty easy to simplify. If we distribute this negative sign to both, so that's going to be negative x times 4.4, so we're still going to get negative 4.4 times 10 to the fourth x equaling this side, which we have 3,000 times 4.184 times the difference between 46.5 minus 25.5, and that gives us 26,359. And then we're going to divide by this. Put it into our trusty calculator. And that gives us, in this case, negative 5.99 grams. Now, mass, we can't have negative grams, so it's implied that this is going to be the absolute value. So we just have 5.99 grams as our answer. Another reason why it came out negative is that they put the sign right here. They gave you a negative sign in the problem, telling you that it was already exothermic, so we didn't really have to put that in this case, but since we're looking for mass, it's an easy fix. So let's see, and I'll do number 12. So let's take a look at number 12. Number 12 says calculate the amount of water at its boiling point vaporized by 152.0 capital C calories. So it wants to know the amount of water. So, well, the equation we can use, because it's only boiling, like it's vaporizing it away, we're going through a phase change, we're not heating it afterwards or anything. So we're going to use our Q equals N delta H, since we have delta H for vaporization on our sheet. We're going to solve for moles first, because we can get from moles to grams. So we have 152 calories equals N times my molar heat of vaporization, which is going to be 9.72 kcal per mole. Now, in case you forgot, capital C is the same as kcal. It's 1,000 calories. So when we divide our 152 by our 9.72, this is going to give us 15.6 moles. And we can take those moles and convert them using our molar mass of water, which is 18 grams, and that's going to give us 281.5 grams is what's needed. So make sure that you read the units very carefully. That'll tell you what you need to do. Well, hopefully you found this helpful, and I will see you later.